This is where we ended up last week. We talked about independence and how independence is estimated. If you have two events A and B, they are considered to be independent if the intersection A-B intersection, the probability of A-B intersection can be given as the multiplication of the two probabilities. And this comes from the conditional probability, which is if you take the probability of B given A, you know that that is equal to the probability of B intersection A divided by PA. So the independence itself says that the probability of A given B is equal to PA. So this is equal to PA, which means that if so now looking back at the independence of events, we can say that the intersection of A and B, the probability of its intersection is equal to the multiplication of the two probabilities PA dot PB. So we can extend that to several events. If the events A1, A2, and all the way up to AN are independent, if and only if for any subset, then the probability of their intersection is equal to the multiplication of those probabilities. So if A and B are independent events, then so are A and the B's complement. So that's what the next line says. If A and B are independent, so if you are given that A and B are independent, then that necessarily means that A and the complement of B are also independent, and A complement and B are also independent, so as A complement and B are also independent, so as the A complement and the B complement. So all these events are independent given that A and B are independent events. So let's look at this example, the second example of this. So it says a red die and a white die are rolled. Okay, a red die and a white die are rolled. So let event A be the event where you get 4 on the red die. So this means that you have say you have the die like this. So this is the red die, and you get 4 on you get 4 on the top, so 4 on the red die. And event B is event B means sum of dice is 7. So for example, this means, let's take another example. Let's say that you have the red die here. Let's say that you get 2 on the top, and then you have the white die. Okay, so white die, and you get 5 on the top. So the sum of these two is equal to 7. So this is the event B. Now if you look at these events, right, the question is, are the events A and B independent? So the question is, are A and B independent? So to prove whether they are independent or not, you have to prove either of those things where P A given B is equal to P A, or P B given A is equal to P B. So how do you approach this question? You have to first of all find all the relevant things in the event space so that are relevant to the question. So what we need to show is whether P A intersection B is equal to P A dot P B, because if this condition is satisfied from the conditional probability theorem, you know that P B given A is equal to P A, or P A given B is equal to P A. So first of all, you need to find out what is PA and PB. So we know the event A. Event A is the circumstance where we get 4 on the red die. So we have 4 here. Now we need to find what will be the probability of A. So we have only one side that contains 4. We have 6 sides. Therefore, the probability of A is equal to 1/6. And similarly, we can think about probability of B. So let's think about the event space that we can see here. You have 6 possible outcomes. You have 1, 2, 3, 4, 5, and 6 from the red die. And from the white die, you have 1, 2, 3, 4, 5, 6 as well. 1, 2, 3, 4, 5, 6. So this is from the white die. Now, let me draw the sample space that you can get. So you can get 1, 1 from the both ends, 1, 2, like this. And you can get this as well. Okay. So you can see that you can altogether get 36 possible outcomes because you have 2 pairs from both dice. Now, the event space says that the sum of 2 dice should be 7. So you can think of, so you can have 1 plus 6. So this is going to be one possible thing in this event space. And then you have 2 plus 5, that is 7. And you have 3 plus 4, 4 plus 3, 5 plus 2 again, and 6 plus 1. So if you look at all the other possible cases in this event space, they will not add up to 7. So you have 1, 2, 3, 4, 5, 6 events out of 36 possible outcomes, which is going to be 1/6 again. Now, let's look at the event space for the probability of A intersection B, and that is going to be the event where you get 4 on the red die, and the sum of the 2 dice is equal to 7. So you get 4 in one instance. So I'm going to go for my red die, and I have 4. So this is all the possible events that can be associated with the event where you get 4 on the red die. And then to come up with event B, where the sum of dice is 7, you have this particular point here. So the probability of A intersection B is equal to 1, because you have only one possible instance in this space, 1/36. Now, actually, you can easily see that this is equal to PA times PB, because if you take a look at PA dot PB, which is the multiplication of the two probabilities, that's going to be 1/6 times 1/6, and that's 36. So you get that this is equal to PA of A intersection B, which is the condition for these two events to be independent. Therefore, you can say thus the events A and B are independent. Okay, now let's go for another example in the next slide here. So it says that you have okay, the next example says that you have a series circuit. So if you look at a series circuit, it means you have, let's say, two bulbs. For example, you have this bulb and then you have another bulb attached series on a series. So if you remember your O-level science knowledge, you know that the if this particular bulb is going to fail, then the other bulb is also going to fail, because the current will not flow from this end to this end if this series circuit fails. So the question says the following circuit operates only if there is a path of functional devices from left to right. So this is your left and this is your right, and if only from left to right all these items are functional, then only the circuit will operate. The question is the probability that each device is functional has been shown. So you can see this is 0.8 and this is 0.9. Assume that devices fail independently. What is the probability that the circuit operates? Which means independently failing inherently imply that the they don't fail together, which means the probability of they are not dependent on each other. So by definition itself, when you get a phrase like this, which means assume that the devices fail independently. So which means if you hear this word that says the devices fail independently, it means that you can directly take the relationship between the probability of L intersection R and their multiplication, which is the probability of L times the probability of R. So L intersection R, the probability of this is equal to the multiplication of the two probabilities independently. So we have been given that this probability is 0.8 and the other probability is 0.9. So you just multiply them and the answer is 0.72, which means there is a 0.72 or 72% chance that the circuit will not operate as you expected. Right. The same type of a question is given in the second part of it with respect to parallel circuits. Now, in the case of parallel circuits, they are actually not independent, because you can see that if one fails, there is a high chance that the other will work. Therefore, you can basically see that they are not independent. So now when they are not independent, we have to go with the condition that there is some sort of a codependency. So we go with that. But in the case of this question, it says assume that devices fail independently. So you have to the, if you get these two devices, you have a probability of 0.9 of failing and this one probability of 0.9. So if T and B denotes events that top and bottom devices are functional, so there is a path if at least one device operates, because they are in the parallel configuration. There is a possibility that even one device fails, the other will work. Therefore, first of all, we need to find out the probability of the total event of either of these things would work. So we have to find the probability of T union B, Divide this T and this is B to indicate top and bottom. So the probability of T union B is equal to 1 minus P of T union B complement, because if you look at event space, you have T and B. So T union B is this one, is equal to 1 minus the other part, which is the complement of T union B, right? So that is equal to 1 minus. So remember from De Morgan's law, the intersection of two complements is equal to the complement of unions. So you can easily say that T union B complement is equal to probability of the intersection between complements. So T complement B complement, and that is going to be because the question itself says that the devices are going to fail independently. Now, don't take this as a confusion. The devices can fail independently, which means in practical conditions, of course, one device in a parallel circuit, one device failing might affect the other device because there will be a change in current and everything. So but this actually means that you can assume that the device will not fail dependently, they will fail independently. Therefore, the condition is that the intersection between the T and B, the top and bottom, is equal to the multiplication of these probabilities, which means 1 minus P of T intersection, T complement intersection B complement is equal to the probability of T complement times the probability of B complement. So since we already know what is the failure probability of each of these devices, that's going to be P of T complement is going to be 1 minus P of T times 1 minus P of B. So we know that P of T is equal to 0.9 and P of B is equal to 0.9. Therefore, we get 1 minus 0.9, that is going to be 0.1. This is 0.1 and this is 0.1. So multiplication would give us 0.99. This is 0.01. So 1 minus 0.01 is equal to 0.99. Okay, so I will skip this part and then I'll go for the next question. So this question is about a class in probability theory consists of 6 men and 4 women. Okay, so the probability class, there is a class. Okay, there is a probability class, right? So a class in probability theory consists of 6 men and 4 women. So you have 6 men and 4 women. An exam is given and the students are ranked according to their performance. So you have altogether 6 men, and so this is 6 men and 4 women. So 6 plus 4, we have 10 students, 10 people there. So there was a class test or an exam and the students are ranked according to their performance, assuming that no 2 students obtain the same score, which means that there cannot be students who get the same score, like 75 each, or someone getting 60 and the other one getting 60. There are no such cases. Assuming that no such cases occur, no 2 students obtain the same score. So the first question is, how many different rankings are possible? So the question, first one, how many different ranks are possible? How many different rankings are possible? So if you think about it, you can see that there are 10 possible choices here. So let's assume that all of them have distinct names. Okay, so if you think about them as individuals and if you assume them as different names, so for example, I'm going to give them names like A, B, C, D. So you have a person called A, and then B, and then you have C, D, E, F, G, H, and 1, 2, 3, 4, 5, 6, 7, 8, and you get I, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. You get J. Yeah. So you have 10 individuals. Now, different rankings means you organize these names or these individuals in different order. So it can be A, B, C, D, E, F, G, H, I, J, like in this order, or it may be A, C, B, D, and all the way up to here, or it may be A, B, C, and then you have H, like this. So you can think of all the possible different variations that can be there. Now, if you look at the problem like this, then for the first rank or the last rank, depending on the way you look at the problem, we'll have 10 options because you have 10 individuals, right? Now, once you choose, because they don't get the same mark, you have to rank them according to distinct rank, because there cannot be people with say 10th position or the say first position or 2 second positions. You don't have that option. Therefore, you have 10 possible choices at the beginning to fill for one of the ranks. Let's start from the first rank. So you have 10 possible individuals, and then for the second rank you have only 9, because after you put 1 at the beginning, then you only have 9 left for the second, and for the third position you have 8 left, and so on and so forth. You will reach the last point with 1 individual. Now, if you look at from 10 to 1, all the way from the different possible options, you can think of by counting principle. You can multiply all these things and come up with the answer. So from mathematical notation, that is the factorial 10, and so the slide says the answer, it is 300 something like 362,880. So it's something like 3,628,800 different rankings are possible. So now it's interesting to see that when you treat them differently, like if you treat them as an individual bunch of people, you have 10 possible options. Now, the next part of the question says that there are if all rankings are considered equally likely. So the second question, or the same, or let's say the second part of the question says, if all rankings are considered equally likely, which means anybody can be at any rank, or it doesn't matter whether it's a boy or a girl, or it doesn't matter, there are no certain rules, anybody can be anybody. So if all rankings are equally likely, what is the probability that women receive the top 4 scores and men receive the rest? So in this case, we have to think about two possible sets inside the 10 possible options. So you have 10 people, but all these 10 individuals are classified into men and women. So we have 6 men and 4 women. So The question says, if all rankings are considered equally likely, what is the probability that women receive the top 4 scores? Which means you can think of it in different ways. So to make it simple, let's think about, you have the positions like this. So these are the first, second, third, and fourth positions. So the question says, so there are remaining 6 positions because there are 10 individuals, and of course when you take 4 women, you have 6 men. So all the other positions, that is 5, 6, 7, 8, 9, and 10, these positions should be filled by men. These positions should be filled by women. Of course, we have only 4 women here, so we are going to fill 4 possible positions. So imagine, forget about the existence of men here. Now, if you look at women, we have 4 women, and we have the first 4 places. Now let's think that you are going to fill one by one to the available positions. So you can start with filling one here. You have 4 possible options, so you fill 4 here, and since you fill 1 out of these 4, you are left with 3, so you have 3 more individuals to fill the second position, and then 2 for the third position, and 1 for the fourth position. Right now, within this first 4, there can be multiple variations. Like you can choose, because you have 4 possible options, 3 possible options, and 2 and 1. The 4 ladies there, they can have different positions, but all of them will have them at the top. So these 4 positions, right? Okay, and then if you look at the remaining 6 positions, you have men to fill. So you have 6, 5, 4, 3, 2, 1. So if you carefully notice, okay, the probability of getting 4 first places, the top 4 scores, the top 4 possible scores, is the same as the probability that they get the last 4 scores as well, because the problem itself is symmetric by definition. So the answer is going to be the probability of four women getting the first 4 scores, and then the remaining men getting the remaining 6 positions, is equal to total number of possible variations, or the arrangements, is 10 factorial, and the possible number of women being in the first 4 places is 4 factorial, and then you have 6 factorial. So you can think of it as like, so you have 4 factorial and 6 factorial here, and you can think of this 10 as 10 times 9 times 8 times 6, so 7 times 6 factorial. So you can just remove it, and then you have 4 times 3 times 2 times 1, divide by 10 times 9 times 8 times 7, so you get, so altogether 210 at the bottom, 1 at the top. So this is the probability. Okay, now the dynamics is going to change if you have more women to fill the first floor, the defined number of places, than the defined number of places. Because if you have 5 women, then you have to choose 4 out of those 5 to fit in here, and then you have 1 extra to fit in here, because that's how it would go. Now we have a similar question in the second example. So the second example states that, use the same paper. So the second example says a committee of 5, a committee of size 5, a committee of size 5 a committee of size 5 is to be selected from a group of 6 men and 9 women. So in this case, we have 6 men and 9 women. So out of these available individuals, you have to select 5. Okay. Now, unlike the previous case, we have to make the choices. So the problem is, if the selection is made randomly, what is the probability that the committee consists of 3 men and 2 women? So what is probability that the committee consists of 3 men and 2 women? 3 men and 2 women. Okay, so we have 6 men and 9 women. We are going to choose 5, and the question asks, what is the probability that the final group will have 3 men and 2 women? So in this case, the possible number of choices, the question is directed towards calculating the probability. So you need to know, if you are looking at the probability, you have to get the number of possible outcomes of the event space and then divide by the n of sample space, n of S. So this is what you need to actually know. So to identify the total number of possible outcomes, you have to think about selecting 5 from all the possible individuals here. So you have 6 men and 9 women, which means we have 15 individuals in our group, in our set. So the possible outcomes of selecting 5 out of all these 15 individuals is equal to, the N of S is equal to 15C5, which means choosing 5 out of 15. So that's going to be 5 factorial, sorry, 15 factorial, 15C5, so that's going to be 5 factorial, and 5 factorial, 15 minus 5 factorial, and sorry, 15, sorry, 15 factorial, 5 factorial, 15 minus 5 factorial, right? So we have that 10 factorial, right? Now, so the other two possible cases is where you have 3 men, you choose 3 men out of the available 6 men. So that's going to be 6C3. Okay. Now here's the thing. Now you choose 3 men out of 6 available men, and you have 9 women, and you are going to choose 2, right? So if you take this one and say plus 9C2, this is wrong, because it's like this: you choose this and you choose this, but you don't consider, by in the previous case we discussed about the multiplication rule, you have options. So along the branches you just multiply, because you have 3 possible options out of 6, 3 possible options out of 6, and 2 possible options out of 9. So this branch, this branch, this branch, and this branch, and this branch. So all the time have this multiplication. So it's like 3 times and then 2 times. So 3 times, 2 times. We have to multiply this. Now the 6C3 is equal to 6 factorial, 3 factorial, 3 factorial. 9C2 is 9 factorial, then 2 factorial, and 7 factorial. So this entire thing, this is the possible choices given the condition. So the condition is that we can have 3 men and 2 women. So this is the possible number of choices given the condition, and this is the total possible events. So the probability, therefore, probability of 3 men and 2 women is going to be this one at the bottom, because it's the total number of all possible outcomes. And then you have 6 out of the, sorry, 3 out of the 6, and then you get 9, sorry, 2 out of the 9. So this is how you get the probability. So if you do your math using your calculators, you get 240 over 1001. So that is the probability of getting 3 men and 2 women from a group of 6 men and 9 women to form a committee of 5. Okay. Now the next thing about the probability is the total probability theorem. So total probability theorem. Right. So the total probability theorem, you can think of it as something that is available. It's you can, if you look at the event space and the sample space, you can sort of identify what this means. Let me show you first. Now, if you look at the event of B, say that you have a sample space like this. This is your sample space. Now, say that you have 2 events. The 2 events are A, B. So this is my A and this is my B. Now, say that I want to write an equation for the probability of B. So if you take a look at the probability of B, it should contain elements inside this. If you look at the probability of A, okay, here, so this is A. Now, if you were to write an equation for the probability of B, you should include this particular part and this little part to quantify or to assess the total probability. Okay, so total probability of B. So from set notation, if you look at the set itself, you can write B as the summation of this, okay, and the summation of this. So it's like PB will be the total probability from the sample space, okay, sample space, entire sample space, and B can be written as the summation of this little part and this little part. Okay, this little part and this little part. So this little part here is actually equal to the probability of A intersection B, because this part is actually the intersection of A and B, right? And if you look at this part, okay, so that is equal to the probability of B intersection A complement. So B intersection A complement means you have say, if you look at the A complement, anything other than A is A complement. So anything other than A, if I may draw it using a different color to make it clear. So if you look at anything other than A, everything else is included. Okay. Now, if you carefully see that this part actually intersect with B. So the probability of B intersecting with A complement is equal to this little part here. So probability of B intersection is intersecting with A complement. Now, if you take this, okay, now what do you have? The probability of B is equal, I'm going to use the notation now, probability of A intersection B plus probability of B intersecting with A complement divided by, this is actually, sorry, you don't need to divide, because this is actually the sample space. So if you take the probability now, this is actually the n number, so this is n total, so you get the probability, right? Now the probability of A intersection B plus the probability of B intersection is A complement. You can take this, so if you take this and look at the probability of B given A, that is equal to probability of A intersection B divided by probability of A. So you can take this part and you can replace it with these two, and the same thing can be applied to the other one as well. So you end up with the probability of B is equal to probability of B given A times A plus here probability of B given A complement times probability of A complement. Okay, so this is the total probability theorem, which means you can basically get the total probability of an event by considering the conditional probability of that with respect to the probability of other events that are within the space that intersect with the other. Hello. Hello, මොකද මම මේ ලෙක්චර් එකේ ඉන්නේ මේකට කෝල් කරන්න එපා මම මේ ලියන ගමන් ඉන්නේ දැන් ඔයා මොකද කරන්නේ එන්න මම දෙන්නම් අතුරු අරගන්න ඔෆිස් එකට එන්න test. Okay, right, basically the probability, the total probability of B can be taken as the probability the conditional probability times the probabilities of the respective other events. So this can be extended, of course, say that for instance B is like this is your B, and imagine that it is inside a sample space like this. So all the other events are like, so this is B, you can have this A, A1, A2, A3 sort of, okay. So this is A2, this is A2, A1, and imagine it like this, okay. So all these other events exist, so this is A1 and this is A2, say that this is A3. If these are the events, then you can actually think of it like you have this part, and this part, So the probability of B is going to be the probability of B given A1 times BA1 plus probability of B given A2 dot BA2 plus the probability of BA given 3 dot BA3, right? And then you have this little part where you have plus the probability of B given, you can go with the complement of all these three, so which means A1 union A2 union A3 complement times A1 union A2 union A3 complement. So you can actually write this. So that's how you write the total probability here.